Okay, we're going to talk about some exponential functions today, starting with exponential growth. So the exponential functions that we looked at yesterday were either growth or decay. The ones that were growing have this thing called a growth factor, where it's basically a value bigger than 1 being raised to your exponent, which if you take something like, 2 to the second, it gets bigger, like grows. That's exponential growth. The initial amount of your exponential function is what you'd have if you plugged in 0 for x. So like this one, anything to the 0 power is 1. So we'd have a starting value of 2. And then the percent increase is how much larger than 1 your growth factor is. So for every increase in your x value, this one's going to increase 25%. So you can think of it as like finding the difference between your growth factor and 1 and then changing that to a percent. Exponential decay is pretty darn similar, except if it's decaying, that means the value being raised to your exponent is less than 1. So my decay factor here is 1/4. My initial amount is still 2. And instead of increasing as my x values increase, it's decreasing. So the difference between my decay factor and 1 here is 75%. So for every increase in my x value, my y's get 75% smaller. And just a reminder, these have asymptotes, horizontal asymptotes, along the x-axis, unless they're translated up or down, which we'll see in a bit. Let's decide if each of these is exponential growth or exponential decay. So first off, you want to look at what's being raised to your power and see if it is greater than 1 or less than 1. So don't just look at it and think if it's a fraction that it's going to be decay, because 3/2 is 1.5, which is larger than 1. And if you raise that to a positive power, it's going to be increasing and getting bigger and bigger and bigger. So it's exponential growth. If you look at B, make sure you're looking at what's being raised to the exponent, not the 1/2 out in front. If I raise 3 to larger and larger powers, it's going to get bigger and bigger in value. So this one's exponential growth 2. So anytime you have a value greater than 1 raised to your exponent, it's growing. If you look at C, that's 0.25 or 1/4, which is less than 1, which means this one is going to be exponential decay. Things are going to get smaller as you increase your exponent. So now we're going to graph some exponential functions, and we're supposed to state whether each is exponential growth or decay. So this first one's exponential growth. Pretty sure this is the only one I remember to actually state that on, but I'll say it in my words now. So if I'm going to graph a function, I just need to plug in some x values and get some y values out. So let's pick a good variety here. Let's go -2 up to +2, and then I'm raising 4 to all those powers. So plug them in. And I'm going to get this for my set of y values out, and then just plot them on my graph. So my scale didn't quite fit to go up to 16. I counted by 2s and then just stuck that one up above. So if you were to do smaller and smaller and smaller x values, it still would never cross the x-axis. So I've got this horizontal asymptote at y equals 0. The only time you're not going to have a horizontal asymptote at y equals 0 is if your function is translated up or down. Now in terms of domain and range, it continues left and right in the positive and negative directions forever and ever, so -infinity to infinity. Now for range, my y values start a little bit bigger than 0. It doesn't actually ever get down to 0, so my range is 0 with the parentheses not including 0, up to infinity. If I do this second one, I'm just going to go ahead and plug in -1, 0, and 1 for my x values. Once you kind of got the general idea for the shape, I think 3 points is good enough. Now remember to raise your value to your exponent before you multiply by 2. So 2 to the negative, 1/2 to the negative first is going to flip it. You're going to have 2 times 2 is 4, and so on. And then plot those on your graph. This is, you can see from your graph or your equation, also going to be an exponential decay function, not exponential growth. And then it's still got that asymptote. I decided to do one more point because I thought it needed one more. And domain and range are the same as the previous one. And then this last one has a translation left to. It is 2/3 to your power, so it is going to be exponential decay. I'm going to do my parent function with my stretch and reflection first and then move it left 2. So that would be what I would recommend if you're doing these. If you have translations up or down, leave those until after you've done your basic points and then change your coordinates in your table. All right, so these are my basic coordinates, and then I need to move everything left 2, which means I'm going to subtract 2 from my x values, and I'll end up with this set of points for my coordinates, which I can plot on my graph. And this one looks a little bit different because it's reflected across the x-axis. So it's not moved up or down, which means it's still going to approach the line y equals 0 for my asymptote. So that kind of tells you what its shape's going to be. It's not going to cross it. Your domain's negative infinity to infinity, and now your range is from negative infinity up towards 0. Now, just as a quick little what-if sort of situation here, let's say that I had a +4 tacked on the end. That would mean it's moved up 4, which will translate your asymptote and all of the coordinates of your points up 4 as well. So your asymptote would be translated up 4 to the line y equals 4, and your range would be negative infinity to 4. Now what's handy is exponential growth models are useful for modeling a lot of real-world situations like interest on your money or population growth. So we're going to look at some exponential growth models here. Exponential growth is where anything's increasing by a fixed amount over a period of time, like increasing at 5% every year or 10% every year. So here we're going to look at some population growth. We want to write an exponential growth model given the population of this county t years after 1970. So I'm going to write my function p of t, a times 1 plus r to the t, and a is your initial starting population. So in 1970, our population was 330,000, so my initial amount is going to be 330,000 people. And then r is my rate of growth, so my population is growing at a rate of 2.4%. So that's my value for r. And then this is just a general model for any amount of years after 1970, so t is going to be a variable. I'm going to simplify this a little bit. I can go ahead and do 1 plus 2.4%. Remember, 2.4% is 0.024. So if I add those together, it's going to be 1.024 to the t power. Now on B, if I'm answering how many people lived in Kern County in 1990, I have to think about T stands for the number of years after my start year, which is 1970. So between 1970 and 1990 is 20 years. So I need to plug in 20 for T. And if you type this in your calculator, make sure you have that 1.024 in parentheses. You should get approximately 530,289 people. You could round to the nearest person. Exponential decay is where your value is decreasing instead of increasing. Essentially, the only change is you're subtracting your rate inside your parentheses instead of adding. So I've got this car that I bought, and after you buy a car, it's losing value pretty quickly. So if I'm writing my model for my car's value after my T years, I started with a value of 25,000. Inside my parentheses, 1 minus my rate of decrease gives me 0.85 to the T power. So after 4 years, if I plug in 4 for T, my car is obviously not going to be worth nearly as much as its starting value. If I was in class, I'd ask you to pause and guess what you think it might be. So you can do that in your head. It's going to end up being $13,050.16. It's a lot of loss in value for 4 years. So compound interest, which you might have calculated in some other classes, is an exponential model. So it looks slightly different from our growth models that we had before because it can be compounded a different amount of times per year, which changes our formula. So in this formula, n is the number of times it's compounded per year. Just a quick little reminder, there are 52 weeks in a year, 12 months in a year, and 365 days. Also, if you see the interest is compounded annually, that just means once per year. So those will come in handy if you're looking at plugging in things to a compound interest formula. Interest can be good or bad. This is the it's not working out so good for you situation because you owe $500 on a credit card, and this is interest that you're going to have to pay to the bank. We'd much rather be earning it on our savings. We are starting with an initial amount owed of $500, so that's my principal, P. My rate of interest is 14.6%, and it is finding the amount after 2 years if our interest is compounded monthly and we make no payments along the way. So compounded monthly means it's going to get compounded 12 times per year. So in my formula down here, my value for n is going to be 12. So if I plug in everything that I've identified, it's going to look like 500 times 1 plus, I'm going to go ahead and change that to a decimal, 0.146 over 12 raised to the 12 times 2 power. And again, when you plug that in your calculator, be super careful. Also put parentheses around that exponent, the 12 times 2, or make sure you multiply it in your head and get 24 first.